Hello and welcome to my lab report. The purpose of this lab is to observe an object that is moving at the same speed without changing direction, or in other words, to observe an object with constant velocity, and then apply Newton's second law to construct a computational model that describes my observations. By rolling a basketball and recording it, I obtained a video of an object moving at constant velocity. Then I put the recording into Tracker and calibrated by using the width of the basketball, which is 0.238 meters. I then went frame by frame, selecting the center of the mass of the ball so that Tracker could find the position time data. From there, by using the first two set of data points from Tracker, I found the initial velocity to be negative 1.08 meters per second. The velocity is negative because I set the axes to where right is positive in the x direction, left is negative in the x direction, up is positive in the y direction, and down is negative in the y direction. Because the ball is traveling left, it has a negative velocity. If I were to flip the axes, the velocity would become positive, so it would become 1.08 meters per second, but the magnitude would stay the same. With the initial velocity in hand, we can begin to create the computational model. However, we need to establish the initial conditions and make some assumptions. First, we set the mass to be 0.567 kilograms, because that is the mass of a standard basketball. Then, we set the position to be 0, 0, 0, because we measured the position of the ball using its center of mass, and we put the origin, or the center of the axes, on the center of the mass of the ball. Therefore, its position will be 0, 0, 0. Then, using the result from the previous calculation, we could set the velocity to be negative 1.08 meters in the x direction and 0 for the other two directions. Now that we've established the initial conditions, we can write the loop that will create the model. Using small time steps, the loop repeatedly applies Newton's second law by updating the ball's position and velocity every time step. We use a small time step so that it will be more accurate. Because we assume f net is 0, the ball's velocity will not change, so the 3D graph of the ball will show it going to the left, and the position time graph of the ball will be a straight line. The loop also gives us a table of position time data, which we will now use to compare the model and our own data from Tracker. Here's the graph comparing the data from the model and the data from the observation on Tracker. As you can see, the model is not 100% accurate. This is because of a variety of reasons. The model uses the first two data points from Tracker to establish a velocity that stays constant throughout the model. This velocity could be wrong for two reasons. Selecting the center of mass on Tracker is subject to human error, and there were other forces on the ball, such as friction, that might have slowed down the ball as it went to the left, which are not represented in the model. The model was created by assuming a zero net force. However, it is not possible to determine how many pushes and pulls were added together to give this zero net force. This is because Newton's second law only relates the net force and the mass's acceleration, and not the number of pushes and pulls.